Okay, so we should be streaming. Let me just double check my input here. Okay, perfect. Solid. Okay, so this is sort of a... Well, actually, I'm going to keep that up. This is sort of day one for something I'd like to get started here. So one thing that I've noticed with learning, as opposed to something like exercise, is that it's not terribly clear when someone is learning correctly or using the best practices for learning. When you exercise, typically, two people are in the gym, one's exerting more effort, you can reasonably assume that one's having a more effective exercise. There's some nuance in that in reality, but if someone's lifting the 5-pound weights versus someone is lifting, like doing curls for the 35s, the 5-pounder, unless they're very weak to begin with, are probably using the wrong weight. But this is in contrast to the hiddenness of learning. So with learning, if you have two students in a lecture, it's not clear which student is having a more effective learning experience. Two students having different learning experiences look pretty similar on the outside because of the hiddenness of learning. And so because of that, and because of the fact that I don't think learning is taught well in schools, I kind of wanted to start this sort of exercise in hopefully teaching learning through primarily examples. Another thing that I think is difficult, or perhaps another current weakness in the teaching of learning, is that it's always taught in abstract ways. So when I was in college, often we would get like a little spiel at the beginning of, or actually not often, there were like a couple of professors that I took that gave a little spiel at the beginning about spaced repetition, maybe active recall, but it was very quick and not very focused on. And the reality is that when you have like a very short experience with it, you're not likely to deeply interact with active learning or spaced repetition and things like that. And that's because I think when something is said, it is not experienced. So with active recall, in specifics, you hear about it, you sort of understand it, but the feeling of it is not purveyed well by just some instruction, right? And so my hope is that as I'm reading, so I guess sort of a summary of what I'll be doing. Speaking of being too abstract with things, I'm going to give an abstract overview of what I'll be doing before I do it. So I'm going to be reading various topics that I don't yet understand, or at least most of them I don't understand. My goal is to learn first person. The book we're going over today is Mathematics, a Very Short Introduction. These books are just money. They're great for a short overview of a topic, and they give you enough breadth of a topic that you sort of have maybe a view from 10,000 feet for a given thing, which is really good because outside of something like this book, it takes forever to get a decent view from 1,000 feet. You could also read a textbook, that would work as well. So the goal is for me to read and show and demonstrate learning, active learning, as well as good metacognitive strategies for learning, and it'll be I'll be doing it firsthand. So hopefully, as I sort of verbalize my thoughts, people will achieve some benefit. Additionally, this is like step one of marketing for a learning management application for self-led learners that I'm developing currently. So eventually, once that's into like an MVP status, or it's minimally working, I'll probably begin to use that on the stream as well. Currently, I use Anki for my learning tools, and pretty much nothing else. I do some daily practices or exercises, or ideally I do some daily exercises for various things that I'm wanting to get better at. But for now, it is mostly Anki when I can get to it, which is not a good thing to say if you wanted to learn when I can get to it. Okay. So yeah, let's go ahead and dive on in. So yeah, well, let's just dive on in. Enough talking. Okay, so we're just starting chapter 1 here. Eventually I'd like to get maybe either I'll screen record and have a Kindle version of a book I read, or I'll have another camera that gives you a display of the book, just so you can look at it and follow along. But for now, I'll just read it to you. Okay, chapter 1, models. Actually, let's see if there's an introduction here. Okay, there is a preface, so let's go back. Preface. In the early 20th century, fair warning, I have read like 4 pages into this. I have pre-read just a little bit. I started it because I was interested in it and realized it'd be very good for something like this. So I stopped and then waited till now. Preface. In the early 20th century, the great mathematician David Hilbert noticed that a number of important mathematical arguments were structurally similar. In fact, he realized that an appropriate level of generality they could be regarded, at an appropriate level of generality, they could be regarded as the same. This observation and others like it gave rise to a new branch of mathematics, and one of its central concepts was named after Hilbert. The notion of a Hilbert space sheds light on much of modern mathematics, from number theory to quantum mechanics, that if you do not know at least the rudiments of Hilbert space theory, then you cannot claim to be a well-educated mathematician. What then is a Hilbert space? In a typical university mathematics course, it is defined as a complete inner product space. Students attending such a course are expected to know from previous courses what an inner product space is, that an inner product space is a vector space equipped with an inner product. I'm going to turn on my light real quick. And that a space is complete if every Cauchy sequence in it converges. Of course, for those definitions to make sense, the students also need to know the definitions of a vector space, inner product, Cauchy sequence, and convergence. To give just one of them, not the longest, a Cauchy sequence is a sequence x1, x2, x3, such that for every positive number e, there exists an integer n, such that for any 2 integers p and q greater than n, the distance from xp to xq is at most e. In short, to have any hope of understanding what a Hilbert space is, you must learn and digest a whole hierarchy of lower-level concepts first. Not surprisingly, this takes time and effort. Since the same is true of many of the most important mathematical ideas, there is a severe limit to what can be achieved by any book that attempts to offer an accessible introduction to mathematics, especially if it be very short. I think this illustrates a really important concept within mathematics, the idea that fundamentals are crucially important. That if you don't understand lower level concepts, that the concepts that are built on those lower level ones will make almost zero sense. So that's a pretty powerful idea. As for the definitions for Cauchy sequence and vector space and all that jazz, that's typically something I would dive deeper into, but because this was more of a narrative demonstration where he was just describing the complexity of sort of pedagogy in mathematics, then I'm not going to go into it. I'll go into further things and dive deep later. Okay, and we'll continue. Instead of trying to find a clever way around this difficulty, I focused on a different barrier to mathematical communication. This one is more philosophical than technical, separates those who are happy with notations, such as infinity, the square root of -1, the 26th dimension, and curved space from those who find them disturbingly paradoxical. It is possible to become comfortable with these ideas without immersing oneself in technicalities, and I shall try to show how. If this book can be said to have a message, it is that one should learn to think abstractly, because by doing so, many philosophical difficulties simply disappear. I explain in detail what I mean by the abstract method in Chapter 2. Chapter 1 concerns a more familiar and related kind of abstraction, the process of distilling the essential features from a real-world problem and thereby turning it into a mathematical one. These two chapters, and Chapter 3, in which I discuss what is meant by a rigorous proof, are about mathematics in general. So one thing that's powerful in learning is to increase something called cognitive load. This is sort of effort. You can think of it's similar to lifting heavier weights if you go to the gym. Cognitive load is powerful I guess the main way cognitive load is powerful, and I guess first I should define what cognitive load is, but is that if you increase good types of cognitive load, you're able to increase the degree to which you understand as well as remember things. So there are a couple types of cognitive load. I'll just speak of them briefly because I'll be describing the concept of cognitive load, or I guess referring to it fairly often, so having a basis is probably good. So there are intrinsic, extrinsic, and germane cognitive load. For intrinsic cognitive load, this is the mental difficulty of approaching an idea. So an example of this would be if I were to teach you what 2 + 2 is and describe addition, it's a fairly easy concept. So the intrinsic cognitive load of that idea is low. However, if I were to teach calculus, which I actually don't understand myself, it would be a much more intrinsically, or a much heavier intrinsic cognitive load for that concept. So intrinsic cognitive load is the difficulty associated with grasping a concept. Then extrinsic cognitive load is anything outside of, or anything that detracts from, anything that detracts from good cognitive load. That's not a great definition, but I'll go more in detail. So extrinsic cognitive load, examples could be playing music or watching TV while you're learning. That cognitive load associated with that distracts you from learning, and thus will almost certainly have a negative effect on your learning outcomes. Another thing would be a teacher that is unable to describe a concept well or teach a concept well. That increases extrinsic cognitive load. You can think of any distractions, anything that's outside of learning that is making learning more difficult. That's actually a good definition. Anything that's outside of the learning thing that is making learning more difficult. And then lastly, germane cognitive load is a good type of cognitive load. So this is the effort that occurs when you encode your thoughts or ideas into long-term memory. So if you think of your brain has multiple memories, I'll just talk about short-term versus long-term. So when I hold like a phone number in my mind and I'm trying to memorize it, the hope is that it transfers from the short-term memory of me, maybe I'm repeating it over and over again in my mind, to the long-term memory, which would be maybe 30 minutes from now, I'm able to describe, or I'm able to say what that phone number was that I was thinking about or trying to memorize. That process of bringing something from short-term memory to long-term memory is called encoding. And if you increase effort in the encoding phase, it helps you remember more. So there are a couple ways that this can be done. mostly is done through a concept called higher order learning, which is anything that enables you to exert more effort in good ways in learning. And just to take a step back, I realized that I'm also giving a more abstract description of these things instead of a more example-based one. So I'll give a few concrete examples, and then I'll be expressing them concretely as I go through. So I guess it is all right that I'm giving a nice abstract, or hopefully a nice abstract definition before we begin. So for germane cognitive load and higher order learning, some examples of higher order learning would be evaluating ideas, comparing and contrasting ideas, determining the strengths and weaknesses, some other examples that also increase cognitive load and that I will be doing as I read through. When a section heading is, or for some section headings, if they're giving an argument briefly, I'll try to come up with their argument, given my brief introduction of that argument, and also figure out the strengths and weaknesses of that argument. So before we even dive into something, we'll try to predict or figure out what their argument might be. This increases cognitive load because it forces you to try to think about sort of the nature of the whole book that you're reading up to that point, and then also what the author might be trying to get at as he or as they are writing. So that increases your cognitive load because you're exerting effort in good ways. And additionally, that sort of prediction or filling out an author's argument before they give it is really powerful because it enables you to exercise the process of building an argument, which is not often done. So that's kind of unique. Okay, so yeah, germane cognitive load, and then we will continue. I'll just read this last couple sentences so we can get back on track. Instead of trying to find a clever way around this difficulty, talking about the hierarchical nature of mathematics where you need to understand lower level concepts before higher level ones, I focused on a different barrier to mathematical communication. This one, which is more philosophical than technical, separates those who are happy with notation such as infinity, the square root of -1, the 26th dimension, and curved space from those who find them disturbingly paradoxical. It is possible to be comfortable with these ideas without immersing oneself in technicalities, and I shall try to show how. If this book can have a message, it is that one should learn to think abstractly, because by doing so, many philosophical difficulties simply disappear. I explain in detail what I mean by the abstract method in Chapter 2. Chapter 1 concerns a more familiar and related kind of abstraction, the process of distilling the essential features from a real-world problem and thereby turning it into a mathematical one. These two chapters, Chapter 3, in which I discuss what is meant by rigorous proof, are about mathematics in general. Thereafter, I shall discuss more specific topics. The last chapter is more about mathematicians than about mathematics, and is therefore somewhat different in character from the others. I recommend reading Chapter 2 before the latter ones, but apart from that, the book is arranged as unhierarchically as possible. I shall not assume, towards the end of the book, that the reader has understood and remembered everything that comes earlier. Very little prior knowledge is needed to read this book. A British GCSE course is equivalent, or its equivalent shall be enough, but I do presuppose some interest on the part of the reader, rather than trying to drum it up myself. For this reason, I have done without anecdotes, cartoons, exclamation marks, jokey chapter titles, or pictures of the Mandelbrot set. I've also avoided such topics as chaos theory and Gödel's theorem, which have a hold on the public imagination out of proportion to their impact on current mathematical research, and which are in any case well treated in many other books. Instead, I've taken more mundane topics and discussed them in detail in order to show how they can be understood in a more sophisticated way. In other words, I've aimed for a depth rather than breadth, and I've tried to convey the appeal of mainstream mathematics by letting it speak for itself. I would like to thank Clay Mathematics Institute and Princeton University for their support and hospitality during part of the writing of the book. I'm very grateful to Gilbert Adair, Rebecca Gowers, Emily Gowers, Patrick Gowers, Joshua Katz, and Edmund Thomas for reading earlier drafts. Though they are too intelligent and well-informed to count as general readers, it's reassuring to know that what I have written is comprehensible to at least some non-mathematicians. Their comments have resulted in many improvements. To Emily, I dedicate this book in the hope that it will give her a small idea of what it is I do all day. Okay. So one thing I'd like to point out before we go on as I was thinking through sort of this preface, is that the author, Thomas Gowers, is intentionally trying to present this book in an unhierarchical manner, which is different than how mathematics is typically taught or presented. So that's interesting. So that part of evaluation, sort of thinking metacognitively, is also increasing cognitive load and exerting effort in good ways. How to throw a stone, Chapter 1, Models. Suppose that you are standing on level ground on a calm day and have in your hand a stone which you would like to throw as far as possible. Given how hard you can throw, the most important decision you must take is the angle at which the stone leaves your hand. If the angle is too flat, then although the stone will have a large horizontal speed, it will land quite soon and will therefore not have a chance to travel very far. If, on the other hand, you throw the stone too high, then it will stay in the air for a long time, but without covering much ground in the process. Clearly, some sort of compromise is needed. The best compromise, which can be worked out using a combination of Newtonian physics and some elementary calculus, turns out to be as neat as one could hope for under the circumstances. The direction of the stone as it leaves your hand should be upwards at an angle of 45 degrees to the horizontal. The same calculations show that the angle the stone will trace out a parabolic curve as it flies through the air, and they tell you how fast it will be traveling at any given moment after it leaves your hand. It seems, therefore, that a combination of science and mathematics enables one to predict the entire behavior of the stone from the moment it is launched until the moment it lands. However, it does so only if one is prepared to make this a number of simplifying assumptions, the main one being that the only force acting on the stone is Earth's gravity, and that this force has the same magnitude and direction everywhere. That is not true, though, because it fails to take into account air resistance, the rotation of the Earth, a small gravitational influence from the Moon, the fact that the Earth's gravitational field is weaker the higher you are, and the gradually changing direction of vertically downwards as you move from one part of the Earth's surface to another. Even if you accept the calculations, the recommendation of 45 degrees is based on another implicit assumption, namely that the speed of the stone as it leaves your hand does not depend on its direction. Again, this is untrue. One can throw a stone harder when the angle is flatter. In the light of these objections, some of which are clearly more serious than others, what attitude should one take towards the calculations and the predictions that follow from them? One approach would be to take as many of the objections into account as possible. However, a much more sensible policy is the exact opposite. Decide at what level of accuracy you need, and then try to achieve it as simply as possible. If you know from experience that a simplifying assumption will only have a small effect on the answer, then you should make that assumption. I like that last section. Decide what level of accuracy you need and then try to achieve it as simply as possible. I'm a software engineer for work, and there's a similar concept in software engineering. Actually, something I talked about earlier. It's something called a minimum viable product. So when you're building something, you try to build the simplest version that would be useful first, so that you can implement it and then iterate on that to add features. This sort of forces you to focus on what's most important or what's most important relative to the features you can provide, as well as focuses directly on application and impact of that thing. It has a focusing effect on your thoughts and your development efforts. And so I feel like this is somewhat similar, where if we're needing, or do we decide how precise, how accurate, we are needing something, and then strip away everything except the most beneficial things for determining, or the things that have the most outsized impact on that accuracy, and strip away those that are more minor. Like that. Continuing. For example, the effect of air resistance on the stone will be fairly small because the stone is small, hard, and reasonably dense. There is not much point in complicating the calculations by taking air resistance into account, when there is likely to be a significant error in the angle at which one ends up throwing the stone anyway. If you want to take that into account, then for most purposes, the following rule of thumb is good enough. The greater the air resistance, the flatter you should make your angle to compensate for it. What is a mathematical model? When one examines the solution to a physical problem, it is often, though not always, possible to draw a clear distinction between the contributions made by science and those made by mathematics. Scientists devise a theory based partly on the results of observations and experiments, and partly on more general considerations such as simplicity and explanatory power. Mathematicians or scientists doing mathematics then investigate the purely logical consequences of the theory. Sometimes these are the results of routine calculations that predict exactly the sorts of phenomena the theory was designed to explain, but occasionally the predictions of a theory can be quite unexpected. If these are later confirmed by the experiment, then one has impressive evidence in the favor of the theory. So this is describing if we have a given thing for which we've made assumptions to explain the theory. And if those assumptions that we made we're able to extrapolate from those other phenomena that are also seen in physical reality, then those assumptions or those assertions that we made initially are given more credence. So if we have a theory, we're assuming some things, we're speculating about the nature of a given thing. And if the mathematics then explain more about the theory, or about the logical results of a theory, and those are found then in nature, then our theory is given more credence. I like that. The notion of confirming a scientific prediction is, however, somewhat problematic because of the need for simplifications of the kind I've been discussing. To take another example, Newton's laws of motion and gravity imply that if you drop two objects from the same height, then they will hit the ground if it is level at the same time. This phenomenon, first pointed out by Galileo, is somewhat counterintuitive. In fact, it is worse than counterintuitive. If you try it for yourself with, say, a golf ball and a table tennis ball, you will find that the golf ball lands first. So, in what sense was Galileo correct? It is, of course, because of the air resistance that we do not regard this little experiment as a refutation of Galileo's theory. I'll pause there. So an example of increase in effort here, I understand the impacts of, or the differences between the golf ball and the tennis ball here. But before the author, Timothy Gowers, gives the explanation, try to figure out or make a guess about what the explanation is. This enables you to practice your ability to create arguments, and also to extrapolate arguments based on not completely clear or maybe ambiguous beginnings, because the author hasn't yet described everything, right? So in this situation, the reason why the golf ball would land, or okay, the golf ball will land first before the table tennis ball, because of the density of the table tennis ball. Because the table tennis ball is so much lighter comparative to its volume, it's less dense and thus can be pushed as it's falling by air resistance, or rather, that's actually incorrect. It's not pushed by air resistance. The air resistance is the same between the golf ball and the table tennis ball, or the ping pong ball, but the ping pong ball, because it's less dense, is more affected, or has less ability to resist the effect of air resistance. And therefore, the golf ball falls faster than the table tennis ball, but if we were in a vacuum, they'd fall at a similar rate. Continuing, it is of course because of air resistance that we do not regard this little experiment as a refutation of Galileo's theory. Experience shows that the theory works well when air resistance is small. If you find it too convenient to let air resistance come to the rescue every time the predictions of Newtonian mechanics are mistaken, then your faith in science and your admiration of Galileo will be restored if you get the chance to watch a feather fall in a vacuum. It really does just drop as a stone would. Nevertheless, because scientific observations are never completely direct and conclusive, we need a better way to describe the relationships between science and mathematics. Mathematicians do not apply scientific theories directly to the world, but rather to models. A model, in this sense, can be thought of as an imaginary, simplified version of the part of the world being studied, one in which exact calculations are possible. In the case of the stone, the relationship between the world and the model is something like the relationship in figures 1 and 2. Just as a description, in figures 1 and 2, there's someone, they're on the beach and they're throwing a football back to each other. The relationship between the stone example is that they're throwing an object, and it's encountering air resistance, and we're determining the path of the object and how far it goes. In this case, the object is the football. One thing that's interesting, so this is the last page that I got up to, so everything else will be new from here on out, is that the nature of models in mathematics and how this has probably changed over time. It's kind of observed tongue-in-cheek that some earlier scientists and academics would be much more confident about their assertions, and obviously a part of it is that our words have gotten much more precise, and we just have to be more couched with our statements because we're trying to reflect reality as much as we can, or hopefully reflect. Our models are hopefully reflecting reality as much as we can. But earlier academics are like, this is the law of everything. This is the law of the universe. All things correspond to this. I've now described every phenomena, kind of thing. And I wonder if this idea of models has developed from this earlier state where we'll say on average academics asserted more and were more confident about their claims, whereas now they're less confident about their claims. So models in this sense, because I guess, models allow us to be more couched in mathematics because we're already from the get-go not asserting that we understand the phenomena completely and that our model, or they're not even arguing that their model is good enough to describe everything about that particular thing. And it may be good enough to, at this level of analysis, to describe it to that degree. But with this model, they are sort of pulling back that hypothetical argument that their model describes everything, saying instead that this is a simplified version of reality. And the thing I also like about that is that if I describe, have a theory, have a model for reality, the model can correspond completely to all the observed phenomena, yet it can still be wrong. So an example of this would be with Newtonian physics compared to something like relativity, where at the given level of analysis of Newton, and even when we got to the moon, Newtonian physics were good enough. They described the world in a sufficient way such that we could control it enough to get to the moon, right? But if we wanted to increase our level of precision, then we'd have to increase level of precision and also explain other phenomena that emerged, or rather, other phenomena that were found that were not explicable by Newtonian physics. And so, thus, the notion of relativity came to be in response to these anomalies. That's the correct word, anomalies. I guess further arguing that from the... Oh, actually, no, I already described that. Okay, continuing on. There are many ways of modeling a given physical situation, and we must use a mixture of experience and further theoretical considerations to decide what a given model is likely to teach us about the world itself. When choosing a model, one priority is to make its behavior correspond closely to the actual observed behavior of the world. However, other factors such as simplicity and mathematical elegance can often be more important. Indeed, there are very useful models with almost no resemblance to the world at all, as some of my examples will illustrate. That is something that I've heard about mathematics and have experienced in some way, that maybe they're called pure maths, maths that are important to mathematicians but have little relevance to the actual world. An example of this would be, searching for prime numbers. A lot of effort has gone into searching for larger and larger primes, and this is a thing done in mathematics for quite some time. And for the longest time, it was useless. Like, it's cool to know primes, numbers that are not, divisible by any other smaller numbers. But it only came in use, and in actually great use, for encryption. Large primes are used for encrypting data and enable secure communications between two individuals over the web and otherwise. So it's interesting. Sometimes in mathematics you have models that are just forever models and you have mathematics that are forever pure mathematics and never applicable. But sometimes, like in the search for primes, it turns out that all this time that we've spent on developing methods for finding primes, all of the time we spent that we've actually spent on actually finding primes, all that was for good because we were able to use it well, or have it eventually became effective, or no, it eventually became applicable to the actual world in meaningful ways. Okay, continuing. Indeed, there are very useful models with almost no resemblance to the world at all, as some of my examples will illustrate. Rolling a pair of dice. If I roll a pair of dice and want to know how they will behave, then experience tells me that there are certain questions it is unrealistic to ask. For example, nobody could be expected to tell me the outcome of a given roll of dice, or a given roll in advance, even if they had expensive technology at their disposal and the dice were rolled by a machine. In contrast, questions of a probabilistic nature, such as how likely is it that the numbers on the dice will add up to 7, can often be answered, and the answers may be useful. For example, if I am playing backgammon for money. For the second sort of question, one can model the situation very simply by representing a roll of the dice as a random choice of one of the following 36 pairs of numbers. And then the author, Timothy Gowers, gives all of the possible number pairs of 2 dice. The first number in each pair represents the number showing on the first die, and the second number in each pair on the second. Since the 6 since exactly 6 of the pairs consist of 2 numbers that add up to 7, the chances of rolling 7 are 6 in 36, or 1 in 6. One might object to this model on the grounds that the dice, when rolled, are obeying Newton's laws, or at least to a very high degree of precision, so the way they land is anything but random, and indeed it could be calculated. So this is arguing, okay, yeah, you do say, or it is correct that when I roll these, it adds up to, the result of the dice adds up to 7, what do you say, 1 in 6? Yeah, 1 in 6 times you roll the dice. But it is also the case, so you're treating it as a probabilistic thing, but it is also the case that if you had all the initial conditions for the dice rolls, that you would be able to understand completely and without the need for guesswork what the result of the dice would be. So if I had the dice, rolled them, had all the initial conditions of the forces that went into it, I could know with high certainty what they would, and what number would be face up at the end after they stopped moving. Okay. However, the phase in principle is being overworked here, since the calculations would be extraordinarily complicated and would need to be based on more precise information about the shape, composition, initial velocities, and rotations of the dice than could ever be measured in practice. Because of this, there is no advantage whatsoever in some more complicated deterministic model. Predicting population growth. The softer sciences, such as biology and economics, are full of mathematical models that are vastly simpler than the phenomena they represent, or even deliberately inaccurate in some ways, but nevertheless are useful and illuminating. We'll stop there. Think about those models and the benefit of those models. So a benefit of those simpler models is that you can get an understanding of the system from a simpler perspective, even if the system is quite complex. For example, in economics, I guess in one area of economics, maybe game theory we'll talk about, there are humans interacting, well, we'll say humans interacting according to, or let's say humans are interacting in some game, and then interacting using the best strategies for the game that they know, and no one human in this interaction could change their strategy such that they like unilaterally win the game. So no one could change such that they just take the dub right off the bat. This is called a Nash equilibrium, or this generates a Nash equilibrium, where if everyone's playing the game, they're using the strategically best actions for the game, then there will be an equal, and additionally, no one individual could change their strategy such that they completely win the game unilaterally. Then there becomes an equilibrium in the actions of the players and the dynamics of the game. So even though humans are much more complex than just entities that follow strategies, it's a useful abstraction because it describes the situation, and you can also derive some understanding from that, even though your model is so much less complex than the actual phenomena of humans interacting in a game. Okay, let's continue. To take a biological example of great economic importance, let us imagine that we wish to predict the population of a country in 20 years' time. One very simple model we might use represents the entire country as a pair of numbers, t-p of t. Here t represents the time, and p of t stands for the size of the population at time t. In addition, we have two numbers, b and d, representing births and death rates. These are defined by the numbers of births and deaths per year as a proportion of the population. Suppose that we know the population at the beginning of the year 2002 is p. According to the model just defined, the number of births and deaths, okay, so we'll stop here. So p, I'm going to try to figure out what the model will be before the author describes it. So we have P of t here, where P represents, so t is time, and P represents a function that converts, or where time is the input and the output is the population at time t. So if we were to describe what P is, it would be how many births and deaths occur at across time t. No. At given time t. How many births and deaths were given at time t? Okay, maybe a simple model, that's fine. So we'll say that the births and deaths linearly increase with time, because if there are more births, there will eventually be more deaths. We'll say that there are no things that cause the birth rate to go down, such that as the population increases, the birth rate also increases. So that across time, we'll have more deaths, but we'll also have more births. Okay, so, let's see, how would that be described mathematically? So the simple way I'm describing it is time times births and time times deaths. So if we're at time 1, and this is represented, 1 unit is, we'll say, a generation. If we're at time 2, then there'll be 2x births and 2x deaths. That's probably not appropriate in terms of actual reality, but in terms of how populations grow. But in the relationship, that's at least, the relationship is at least superficially okay. Okay, let's continue. According to the model just defined, the number of births and deaths during the year will be birth times P and death times P respectively. So the population at the beginning of 2003 will be P plus BP minus DP equals 1 plus B minus DP. Okay, so this is good. So the nice thing about making a prediction about something is that you can understand where you are wrong for a given prediction. So yes, it is the case that I was able to connect the idea that as time increases, both deaths, if we're in a really simple world of, if we're in a really simple world, then as time increases, deaths will increase because the population grows and more people die, and births will increase because the population grows and more people will be born. So I described that, but the author was describing the population. I was just describing how it relates to things. So the deaths, if we're wanting to describe the population and not just the amount of births and deaths, then the deaths of the population will decrease the population and the births will obviously increase it. Okay, so additionally, he made an emphasis on being able to input a particular number or a particular date and have an output of the particular population. Though I loosely talked about that, it's important to note that that was specifically stated. So in that, I can sort of tune how I'm thinking about mathematics in that, and obviously so, well, not obviously so, but now obviously so, we focus a lot on functions, we focus a lot on functions and inputs and outputs. Okay, this argument works for any year, describing the model that predicts based off births and deaths, or sorry, based off time, the population. This argument works for any year, so we have the formula P in parentheses n plus 1 equals 1 plus B minus D, close parentheses, P of n. Okay. Okay, so this argument works for any year, so we have the formula P of n plus 1 equals, oh, okay. So P of n is the function of n, where n is the time, and P's output is the population, right? So we're saying here, if all things are equal, then a function that has n plus 1 additional year will be the function of n plus any births or deaths that occurred within the year and the year. No, plus the births and deaths that occurred within the year. I think that's reasonable. Yeah, I think I'm going to give the camera probably next session so you can see what I'm seeing, because I could describe better. Because there's actually, maybe, no, we won't go into it. There's one thing that I'm not entirely understanding about this. Maybe I can describe it. So, I'll just, yeah, I guess we'll have to figure out how to do this at some point. So, sometime now is better than never. Okay, or rather, now is as good as ever. So I will make myself small, and then I'm going to we'll remove this one. Yes, I'll add a window capture for this window. Okay, so you should be seeing the window capture, and now you should be seeing me. Dope. Oh, let's see. I kind of want to make this smaller so you can see everything. Okay, we'll just go with that. Okay, so I have some borders issues right here, but we're chilling. Okay, so we're gonna move over here. Okay, so and this will probably be, let's see, how far do I want to go? I think I will end at the behavior of gases. So that's only 8 pages or so, but we started a little late, or I started a little late, and then this was good. Okay, so for the thing he's describing. So this sort of action that I'm taking right now is really beneficial. I've identified something I don't understand, and I'm diving deeper into it. So I'll first, I think that's large enough. Maybe can I Control plus? Okay, this is Control plus. Yeah, I guess it's reasonably large. Okay, we will put this here. Okay, so this is the formula that Timothy Gowers, or Gowers, presents P of n plus 1 equals 1 plus 1 plus b minus d, 1 plus b minus d, and then P of n. Okay, so think about, yeah, I still don't super understand this here. Okay, so the issue I'm having here, I'm gonna move me a little bit. Okay, no, we're chilling. The issue I'm having here is how he's equivocating these two things. So if I have of p of n plus 1, that is p of n plus p of 1. If I'm thinking about this correctly, so that would be, I'm actually going to move this back this way. So that would be p of n plus p of 1. If that is, let's see, can I distribute a function across? Oh, I'm not sure if I can do that. Yeah, so this would be, this is an important consideration. So if this were, instead of it being a function, if this were a coefficient or a variable like x, I could easily, I can't remember which property it is, but look it up. Distributive property of multiplication, maybe? Okay. So we'll just go to the Bard, and we'll see if we get any. So it is in fact the distributive property of multiplication. So if I'm multiplying something, if this was, instead of it being a function, if this were a variable, then I could distribute these two things such that it would be p times n plus p times 1. But I'm not sure if I can do that with a function. Yeah, I don't think it's the case that I could do that. So my guess is that it's no. Bard may lie to us, or I see, it's Gemini now. Gemini may lie to us, but we'll see what they say, what it says. Have a function p. The input of function p is p n plus 1. If p were not a function, but instead a variable, I could distribute the variable x, p, variable to both n and 1 by the distributive property, of multiplication. Distributive property of multiplication. Can I do this with functions? Okay. So from my, if I were to take this from a computer science perspective, rather than, oh, I guess one type of computer science perspective of a function, rather than a mathematical perspective. So one difference between pure maths and, math and computer science is the nature of a function. So my understanding of mathematics is that a function maps a domain of inputs to a domain of outputs. So maybe if we had an inputs of 1 through 4, and the function was to double the inputs, then we'd have 2, 4, 6, and 8. And the domain of inputs would be 1 through 4, and then the domain of outputs would be those that I just described. So I don't think it's the case. In computer science, that is not the case, the domain of inputs to domain of outputs. You can have something called side effects, which play a role in sort of ensuring that the domain of inputs doesn't directly map to a domain of outputs. Perhaps that's another thing I can look into later. but I don't want to get too distracted. But my guess right now is that it's not the case that I could do this. Aha. Okay. Okay, so functions aren't scalars. Oh. Okay. So anyway, so right here we're describing P of n, we're equivocating P of n plus 1 to P of n plus 1 or times 1 plus births minus deaths. So in this case, we're multiplying it? Yeah, I don't particularly understand this, because if it is the case that the effect of 1 year is merely this, it doesn't make sense that we're multiplying it, right? So if I'm doing P of n plus 1, and this is 2004, and this is 2003, if I get the population at 2003 and I have the population at 2004, it doesn't make sense to multiply my population of birth minus deaths with the unless these aren't. If this may work if these are not actual births and deaths, but rather they're the proportion of births and proportion of deaths. Let's see if that works. So if I have births and deaths as proportions of the population, so instead of saying my population is 10, instead of saying my population is 10, what I'm saying here is that, oh, I think we're onto it. I think this is it, actually. Okay, so here we have birth minus death. So we could say the proportion of the new population that's born and the proportion of the new population that dies. And so in that sense, it makes sense that we're doing births minus deaths. So let's give a population of 10 people. There's going to be 2 births and 1 death. So we're going to be left with 10% of the population will increase because 2 people have been born, 1 person has died. The 2 people that were born count as 1 additional because someone died. Okay, and so, yeah, this is it. Okay, so since we have the proportion of births, the proportion of population change for births is this, minus deaths is for that, and then we add 1 because we're taking the entirety of this population plus the increased or decreased proportion according to the births and deaths. So I'm just going to make this a little bit more explicit, and then I think we'll stop the stream after that. Okay, so we'll say 1 plus 1 plus 0.2 minus 0.1, and say we have a population of 10 people. Of 10. Okay, so and then Population of 2003. Okay, so we'll say that we have the population of 10 at 2003. The percentage of the population that was born was 0.2% of the, or sorry, is 20% of the population, and the percentage of the population that died was 10% of the population, represented by 0.1. Okay, so we're going to subtract those that died from those that were born because we are just caring about how this affects the population, and then we add 1 because we want, when we're multiplying things, if we have this percentage, if I was only to have the 0.1 here, I would end up, because 0.1 is equal to 10%, I would only end up with 10% of the population of 2003. But since I want the entire population of 2003 plus the change that occurred, I'm going to do 1 plus whatever change occurred according to the percentage of the population. I think that was pretty good. Okay, so what I learned here. Okay, so we're another metacognition. I'm evaluating what I've learned here. So the author here is describing that p, or the function p of n plus 1 is equal to p of n, which would evaluate the population at a given time, plus the births that occurred, the proportion of births that occurred minus the proportion of deaths that occurred, plus 1 year, because if we're multiplying these two things, then we want the entire 2003, which is represented by 1, or 100%, plus the 10% that we arrive at from the births, which is, or the 10% of population growth we arrive at from having birth, or from taking the births and subtracting the deaths that occurred. Okay, I think that was excellent. Okay, sweet. So I'm going to, let's see, we'll go back to this, and then I'll make myself big, center myself. Okay, and for these things I will get better at, I'm sure there are some features where you can snap to like presets that you have. I'm using OBS for the software for this. So, okay, let's continue. So I'm just going to read this last section, and then we'll end the stream there. Okay, meaning that the population at the beginning of the year, so this is right after he gives the right after he gives the formula that we just discussed. This argument works for any year, so that if we have the formula, insert formula here, meaning that the population at the beginning of the year, n plus 1, is 1 plus b minus d times the population at the beginning of the year n. In other words, each year the population multiplies by 1 plus b minus d. It follows that in 20 years, it multiplies by 1 plus b minus d to the 20th, which gives an answer to our original question. Even this basic model is good enough to persuade us that if birth rate is significantly higher than the death rate, then the population will grow extremely rapidly. However, it is also unrealistic in ways that it can make predictions very inaccurate. For example, the assumption that birth and death rates will remain the same for 20 years is not very plausible, since in the past they have been affected by social changes and political events, such as improvements in medicine, new diseases, increases in the average age at which women start to have children, tax incentives, and occasional large-scale wars. Another reason to expect birth and death rates to vary over time is that the ages of people in the country may be distributed rather unevenly. For example, if there had been a baby boom 15 years earlier, then there is some reason to expect the birth rate to rise in 10 to 15 years' time. It is therefore tempting to complicate the model by introducing other factors. One could have a birth and death rates b of t and d of t that varied over time instead of a single number p of t, representing the size of the population. One might also like to know how many people there are in various age groups, It would also be helpful to know as much as possible about social attitudes and behavior in these age groups in order to predict what future birth and death rates are likely to be. Obtaining this sort of statistical information is expensive and difficult, but this information obtained can greatly improve the accuracy of one's predictions. For this reason, no single model stands out as better than all others. No single model stands out better than all others. Oh, maybe he's describing that there are some trade-offs. Because the statistical information of, or rather, the effort and money required to gather statistical information such that the model could have more fine and more variable, or more variables generally would make it more complex and maybe less easy to arrive at. But for the simpler models, though they're simpler and you're making some assumptions, just like you are in the more complex model, but less so, more so, because of the simplicity, there's also benefit in that as well. So you can, yeah, okay, I think that's good. As for social, or I guess that is to say, some models are used according to the context they're needed in. So if you need high predictive accuracy and you have like a shitload of money, then it's reasonable to spend the money to get what you need, because you require it, that you require more accuracy, and hopefully you can get at that by understanding the population better. Additionally, the simpler model is also nice, because if you're in class and you're wanting to learn about birth rates and death rates, you can develop an intuition for what occurs when birth rates are high, and what occurs to a population across time when death rates are high, and the combinations of those. And you don't have to gather a lot of information. So better in the sense is the effectiveness of the, or let's see, when he describes better, he's meaning that there is no absolutely better one model, because models are used and are useful according to the context for which they're used in. Okay, as for social and political changes, it is impossible to say with any certainty what they will be. Therefore, the most one can reasonably ask of any model is predictions of a conditional kind, that is, ones that tell us what the effects of social and political changes will be if they happen. Okay, that is up to the behavior of gases on page 8. So I'm going to end there. One more thing as I sort of close, I just had this thought. So this sort of studying or learning, this exercise is longer than if I were just to speed read, like zoom through the material, right? There are like a few things that that I would have like spent more time on, and obviously reading something out loud is going to take longer because I can't increase my speaking speed as much as I could increase my reading speed. But this sort of study that I'm doing is not indicative of what the studying ought to look like in the fact that I'm reading aloud, right? I think a good rule of thumb is to go faster in areas where you need it less, and go slower in areas where you need to interact with the material more. Just like the models. If you need a simple model, you don't have to collect a lot of information, but if you need a more complex model or have greater need, then it is beneficial to use a more complex model, or go slower in this case. Well, perfect. I think that was an excellent and successful stream 1. And I am excited and ready for many more. As for future plans, I'd like to, of course, finish this book. Since we did 10 pages today, or about 10 pages with the preface included. And this book is about 120 pages long. Let's double check that. 130 maybe. 140 maybe? Yeah, about 140. That's about 14 sessions. Things could speed up, things could slow down, but I'm not partial anyway. I'll be here. Well, thank you for watching, if you have watched this, and I will see you next time. Oh, actually, before I go. As for frequency, my schedule is not set in stone yet. I'll probably increase regularity for which I stream, be more consistent, all that jazz. I'm planning on streaming Wednesday night and also Saturday afternoon. I'll probably, yeah, that's kind of all I know for now. Adios.